So we started with Maxwell-Boltzmann, and I'm going to kind of jump around a little bit in time because I can, and it'll hopefully make a little bit more sense. And you know that a probability distribution is not necessarily probability, right? You need to take a probability distribution, multiply it by a spread, and then integrate it to equal probability. And when it came to, so in terms of, we had the first example in the first day of coins, and then there's that write-up that I gave you, chapter 10 of the book that's still in production. So you might want to look on that. Look at about how probability distributions are different than probabilities. In terms of how nature distributes things, nature distributes energy via the Boltzmann equation. And remember, KBT is like nature's energy yardstick. And here you go. Here it is. The probability of a certain energy, I. And don't forget that we have two different E's. We have two different E's. We have E for energy, which makes sense, but we have E for electric field in the Planck distribution. Don't forget that. Planck distribution is not a big part of this test. It's only one question, because that's a weird one. But anyway, so this is a Boltzmann distribution. And let's see, now don't forget that, so this is kind of like the umph of the equation, and this is the normalizer. That's the part you really want to remember. That's the normalizer. And hopefully this part makes a little bit more sense, the normalizer. Now that we're covering things like particle in a box, quantum mechanical particle in the box, remember how he's telling you that you have to have the waves fit? And so this is like the ground state wave function of a particle in a box. And then there's the first excited state, which looks like that. And then there's the second excited state, which looks like that. And these have different energies, and they're quantized in little steps. So I'm hoping when you see stuff like this, this part, this normalizer actually makes a little bit more sense. You can see how there would be in any real chemical system where quantum mechanics is in charge, there are actually discrete quantized energy levels that can be summed up or summed into the I summed up. And there you go. And remember that this is what makes all those Maxwell-Boltzmann integrals equal to 1. Okay, now so what? All right, Maxwell-Boltzmann by itself, whatever it does, Maxwell-Boltzmann is when this has velocity in it. This is Boltzmann. It's I want to keep it straight. Anyway, whatever the Boltzmann equation does, it is presently doing it. There it is. And it's kind of like, all right, but so what? There really is nothing else to do with this as it stands. So when we start applying it to different things, what you do is you shove other expressions in for the energy. And those expressions have other things in them. And what you learn are about those other things, right? Like velocity, or again, I'm going to skip around in time. Let's talk about photons. Okay, I can plug in the energy of a photon into the Boltzmann distribution equation, and I start to learn about, that's hc over lambda. Right? Which, of course, c over lambda is the frequency. So there's a Planck's constant times frequency like you've always seen it before. But now one of the things that we found out when we were doing Planck distribution is that this isn't really the energy. We're talking about like a little light bulb. This isn't really the energy because nature can add multiple photons. So when you plug this into the Boltzmann distribution, it's no longer telling you about energy, it now tells you about average number of photons. But isn't that the same thing as energy? It is, because you can put it into this formula. So that's the trickery with this. Taking the Boltzmann distribution, plugging an expression in for energy, and now you're learning about those other things. Okay, so that was photons, a number of photons, and then for Maxwell-Boltzmann, the Maxwell part is velocity. So I'll just write Maxwell, and that's when energy is 1/2 mv squared, which is not hard to remember that. And what we end up with is the Maxwell-Boltzmann. Now I'm going to write this in a very funky way. I'm going to put some mixed dimensionality here. we've got e to the minus mv squared over 2 kBt. The 2 is, of course, from the half. Now that's net velocity, and then what you have is the sum of all the other energies, and we got into some funkiness here because I got to remind you that you actually live in 3 dimensions, so I have to write down 3 different integrals. Let me just do this because it's kind of stupid to write the same thing down again, otherwise I'm going to spend all time on it. So anyway, now we have to know what the proper limits are. In the questions on the exam, when I do silly things like piggies or grades, I make sure I explicitly tell you what you need to know, because it's already in your question. I don't want to make it frustrating, right? So just trying to figure out whether you really understand this stuff. So, okay, so when it came to trying to learn about velocity by plugging in velocity into energies, we get this thing, and again, this part is the normalizer, and this part is still actually, v squared is really vx squared plus vy squared plus vz squared. I'm not writing it that way because I don't want to deal with it in that manner. What ends up happening is this stuff on the bottom ends up being 2 kBt. This stuff on the bottom ends up being 2 pi kBt over m. Now I get 1/2 for every integral is to the half, but there's 3 of them. So there you go. And don't forget though, then I've got a dvx, dvy. Sorry, I picked up these partials. I actually should have had them, when I wrote down this integral expression, I actually should have had them here. So sorry about that. That's a detail, it's not important. It's not important to the exam. Okay, so there's that. Now let's do some fixing. Let's put this in the way that you were used to with m over 2 pi kBt. Now, in terms of the exam, of course, you have a Maxwell-Boltzmann distribution of grade, something like that, and you've got to set it up correctly and look for the calc identity. I'll send you the cheat sheet right after. I solved this with the calc identity, this to the half, but then there's 3 of them, I just said that. Calc identities, look for the calc identities, because again, I don't want to make the test just trivial, but calc identities exist on the internet, so you can find them. So anyway, just saying, minus mv squared over 2k2, 2kbt. Seem to be remembering the kbt. Okay, now the next thing we dealt with was how to turn these partials. So remember that, okay, I have partials, so I have to do integrals, but when you have a partial, those partials, if those partials are hiding in a variable, we've seen this many times, if there's a Vx in here, I need to draw it out. I need to draw it out because I can't ignore it when I'm doing an integral. Remember how when we were doing work, we had minus PdV, but remember that for work? But pressure had volume inside of it, so we had to get that out of it so that we could do the integral properly. Well, V squared, V, has a Vx and a Vy and a Vz in it. So that's a problem. So either I can re-express this as Vx squared plus Vy squared plus Vz squared, and we did that. We actually did some problems with that, although I haven't done that on this test. Or we did that. The other thing to do is to turn this into net velocity, which was actually if you look at that chapter of the book that I put up on the web, which I wrote kind of quickly. It's not very polished, but what you're really doing is turning this into spherical coordinates and integrating out the angles. That's a really rigorous mathematical way to do it. That's how you do it properly. In class, what I showed you was how to think of this as a growing sphere. Right? So the sphere grows as the partial of R. And this is a growing volume element, the growing volume element of a sphere. And the growing volume, I can't believe how well that came out. Anyway, the growing volume element of a sphere is a shell. It's the volume of a shell. And so I know that the surface area is 4 pi r squared. The surface area times the thickness is the volume of the shell. So this ends up just being 4 pi r squared. Now, two ways to do it. Either you can solve the brute force mathematical Jacobian, which I show you how to do if you really want to. You should have seen that in calc class, and if you didn't or you don't remember, it's in that thing I gave you in the appendix. Or you see this as a growing volume with circular symmetry, spherical symmetry, and every time we take a step in integral space, we're really just multiplying the function times a shell volume, and that's the formula for a shell volume. So that's again, two ways to think about it. Let's see, now what did we do with this in this form? Now, of course, this is the part, there's three things that happened. One is you have to make sure, now I don't have you do this on the test, but knowing the proper limits, again, it's a little funky that you know the proper limits. I know it can be a little frustrating that if we're doing x, y, and z, the proper lower limit is minus infinity, the upper limit is infinity, but when we're doing net, the proper lower is 0 and the upper is still infinity. And again, I make it clear on the exam what are the proper limits, because I don't want you to get hung up on that. So, okay, what do we have? We got 4 pi v squared, and again, that's the Jacobian, that's making sure that our volume element is properly represented from 3 dimensions to 1 dimension. So that's the Jacobian. Here's the normalizer.
Is it v squared or r squared?
V squared. Now remember, don't forget, sorry. And I did this when I did this in class. I don't quite ever know how to get this right. You're used to x, y, and z, so am I. And we go from x, y, z to r, theta, and phi, so I expressed it that way. But it's just vx, vy, and vz. It's the same thing, they're just letters, and they still have x, y, and z in them. And the net is no longer r, but maybe I should call it v sub r, right? But it's just v for net velocity. And I get those, you just saw me get those confused. Sorry about that. So, right, there is no r in this. Just net velocity. It's v instead of r. Yeah, okay, got it. Okay, any other questions? I thought I saw somebody where, okay, so, Jacobian, volume element, 3D to 1D fixer, that's what that does. All of those things I just said were correct. M over 2 pi kBt, that is what makes this normalized. Here's the business end. 1/2 mv squared, 1/2 mv squared is energy, and of course it's always weighed by kBt, and there we go. Okay, now what is this? Now here's another way to look at this. I've written a number. The reason I call it a number is because it's a discrete, it's a, what do you call it, integral with limits.
Definite integral.
A definite integral, it's a definite integral. This is a number. If I ever write a definite integral, it's a number. It's not a function, it's not v half, right? It's, what is it? 1. Average velocity. Right. No, it's 1. It's 1. Be careful about this, right? And I told you, it's the thing to be careful of. This is the integrated probability distribution. The way to express this in words is, what is the probability that you're either not moving or are moving? The probability is 1. You're either moving or not moving. Of course you are. Now, one of you just said is the average velocity. You take probability distributions and multiply them by the thing you want the average of. Sorry, MV, right? MV is, I do that on the test, Maxwell-Boltzmann, MV. This is average velocity. Right. Now,
What would be your limits for that?
that's still same limits. Same limits. Let me be a little bit more explicit. We have a bunch of constants. We have a v cubed. That is the part that will mess you up. You do have to find the right calc identity. It's all about finding the calc identity. don't worry about the constants. I know that it looks mind-blowing, but when you just say, take them out of the integral, and I do that by just calling them a single letter, and of course, well here, let me just be very explicit. This is 4 pi m over 2 pi kbt. Okay, yeah, there you go. And now I know that what I'm looking for, I look in the cheat sheet, I need to have the right limit, and again, it's being error checked. I give you what I find on the internet. There may be an x squared in the cheat sheet, and I will be sending that right after class. I'm giving you again what I find on the internet. You just have to use it properly, you have to identify, you have to remember not to forget your constants. You have to not forget your constants that just carry through. Then you have to identify, let's see, do I actually have this? I think this is 1 over the square, 1 over 2a squared. And of course, A is, what is it, m over 2 kbt. Sorry, my handwriting is turning awful. Yeah, there you go. So you get the Maxwell-Boltzmann distribution. Try to don't be bothered by the constants, but don't forget them either. So what you need to recognize is the underlying symmetry, so that you can Google or look in the cheat sheet for the proper identity. Again, not forgetting the constants. In this case, it's 1 over 2a, where a is m over 2kt, and you're done, right? Now don't write this down, okay? But another mistake, this is a rare mistake, but 1 or 2 of you will make it every year, that you then apply limits to this. Don't do that, don't do that. The limits have already been applied. Now, I do have a question though, where I give the identity, and that's actually a quantum question, where I give the identity as an indefinite integral, and you then have to apply the limits. So, because I wanted you to, I kind of want to make sure that you can still do that.
Can you repeat that?
Okay, so be careful in this, so I just did the average velocity, and again, if I've done this right, at this point it's an algebraic nightmare, but what it ends up being is 8 kbt over pi m. I just happen to remember this. So plug in this 1 over 2a squared is this, and simplify it, you're going to get this. Remember on the exam, don't simplify anything, and we'll fix any TA mistakes if they make that kind of mistake. You guys, as I've said a million times, you don't have to simplify anything, although I think the TA's messed up a little bit on some of your homeworks.
You said on the test you'd have a question where you give an identity without limits.
Right. So I do have one of these because I did want to make certain that. So I have something like this on the cheat sheet. So for one of the questions, it's like this is the right guy, but I have it as an indefinite integral. So what you need to do is then apply whatever the limits are. Call it A and B. You need to be able to do that. Right. So when you see the question, you may be thinking like, why the heck did I do that? When you see the question, you'll understand. Anyway, so I'm just going to drop it there. I'm kind of hemorrhaging a little too much here, but so again, it's just that I only brought that up because sometimes I see people try to apply limits here, which you shouldn't because they've already been applied. Plus there's no place to put them in. These are all a bunch of constants. I don't know how you could apply limits to that. There's nothing to put the limits into. So anyway, we're all okay.
I have a quick question. Going back, can you repeat? You said for the probability, say for the energy, you can use the energy equation of a photon, and that gives us what exactly of the photon, the number of photons there?
Well, in this case, now again, to be a little practical, I have not, and I never do, had much beyond the descriptive question, so like a explain in words question on the Planck distribution, because it's not that hard, but it's so weird how many things are happening at once with modes and degeneracies and Boltzmann distribution, all of them happening at the same time. It gets a little confusing. Regardless, though, what you do with this When it comes to, let's do the average energy of a photon. I'll put that as a little subscript. How you do that, and this is a good question because you do have an average, you have to do average grades on the exam. So I throw a distribution at you and say, hey, give me this average, it's average grades. Anyway, you'll see it. And I've done that before, trust me, and I know that. I wrote a different question, I wrote a different distribution question than I've done in the past. I've done average grades before, maybe at my old exam. Okay, anyway. All right, so what? How do you do it? Well, there's the normalizer. Now the sum is, remember that when you shove something into the energy equation, it no longer is about energy, it's what you shoved into it. Just like I learned all this stuff about velocity when I shoved velocity in for energy. When it comes to photon energies, I have hc over lambda. Okay, that's the energy. Oh, wait. Now, number of photons. See, now it's about number of photons. And let's not forget the minus sign, which comes with the Boltzmann equation, or the KT that comes with the Boltzmann equation. So now, because I shoved this thing into the Boltzmann equation, it's no longer about energy, but number of photons. So the summation is now over number of photons, and the guy on top is exact. Now, the guy on bottom and the guy on top are always the same, by the way. That doesn't make any sense if they weren't. That's not particular to this particular problem. Okay, so now I've got the Boltzmann equation for photons, or number of photons. Again, it's now about something else. Now that I plug an expression into the energy, what we did with this, there is an identity for this, and so on that handout I sent you, I showed you what this evaluates into. Okay, so this is still a distribution.
But you said that was average energy.
No, well, no. This is just the Boltzmann distribution. I haven't done anything. This is just the Boltzmann distribution. By itself, it doesn't really do anything. I haven't turned into average photons yet. This is the business end of the Boltzmann distribution. This is the normalizer. I haven't done anything with it yet. So let me do something with it. Let's do average photon energy. And so I take this distribution and I multiply it by the thing I want the average of, which is photon energy. There we go. All right, last bit, I have to, sorry, I'm not using the board too well. Last bit, we have to do the equivalent of an integral. And again, this is why I actually tend not to put Planck distribution questions on the test, is because it's slightly easier than quantum mechanics, but it's so different than the velocity thing. I really hate for you to get confused. So, I mean, just look at this. This is hideous, right? It's hideous. Recall that this is actually just an expression at this point. So it's not like I'm really doing two sums. This is evaluated into some function. And then there's this part up here, and then you get the answer, which I don't quite recall off the top of my head. But identity turns into a function, and then this is an identity, which then gives the answer. And again, set up the Boltzmann distribution times the thing you want the average of, and then integrate. In this case, you don't actually need to integrate the sum. It still works as a sum. Again, it's a little different, and I hope that's not too confusing, but that is how it works. Question?
It's just the sum on top, right? It's not the sum of the whole thing?
Well, now remember, this part here is just an expression. I can, let's call it the normalization. Let's call it the normalization thing, which is just a function of lambda. And then I've got, in fact, I even think I remember it. I think it's 1 minus hc over lambda kt. In fact, I think that's what this ends up being here. So there you go. It's just a function. And then there's an identity for this. And then this gives you, unfortunately I don't have it in front of me, this gives you the average photon energy. It's 1 over e to the lambda kt, blah, blah, blah. not complicated, but, question?
Relating these back to the average velocity on the top one, is that
Uh-huh.
why you have, bring it back,
Yeah, bring it back down.
is
Oh,
that why you have the DQ, because it's just that?
what?
Is that why you have the velocity cubed, because you just took that?
Because I multiplied it by
Yeah.
velocity, so there's a velocity cubed.
So that's the Maxwell-Boltzmann distribution times what we want to find the average of.
Right, so this is still 1 because this is the integrated Maxwell-Boltzmann distribution. Then I multiplied it by the thing I want the average of. I'm not expressing it the same way because I'm trying to get you to answer the question by trying to block out all those constants, which really just kind of make your head hurt. Block them out, but don't forget them. Identify the calc identity, Google it, but look on the cheat sheet. And then you're at the answer. It's that easy.
Would that one need a normalizer too?
It has, that's the normalizer right here, remember?
Oh,
Remember, this is the Jacobian part. That's the thing that goes from 3D to 2D, to 1D. This is the normalizer from the Boltzmann distribution. This is the business end, and this is just the spread. Remember, just look at the first video, literally the first lecture video, and I broke all this down. And then you just get it into the identity and identify the identity, and you're literally done. Question?
So these are merely two different ways of getting an average value, one doing a summation with the Boltzmann.
These are the same. No, they're not different. They are exactly the same. It's just that the mathematical route diverge. These are both distributions times the thing, but velocity has to be integrated because we think of velocity as being continuous. Right, so velocity can be 1 meter per second, 1.01, 1.02, 1.03, but photons, instead of this being an integral, it ends up being a sum because
They're discrete.
right, because it's a discrete sum. There's either 0 photons or 1 photons or 2 photons. That's why there's this divergence, and again, this is why I don't have, this is not on the exam, by the way, because I know that that's like, what? What am I summing? What am I integrating? You integrate when you have a continuous variable, you sum when you don't. It's quite clear to someone like myself who's been doing this 20 years, but you're seeing this for the first time. So I tend to default towards the questions like this nature, because again, it's, you know, you need to see the Planck distribution. It's traditionally part of this course, but it unfortunately looks very different. It really isn't. It looks different though, so I tend to not put this on the test. Other questions? Okay, last bit on this. Okay, I don't have a normalization question. I don't have that. It's a nice math question. I do have one pure math question as an extra credit, just for the hell of it. But I tend not to put normalization questions because they should be normalized, and it's just a little silly. Recall that when I do ask a real question, which is an average value question, I always have average value questions, and I have one of the derivational questions is an average value question. If you've done it wrong, you'll get the number 1, right? That means that you forgot to multiply. If you take this expression, I say, hey, what's the average value of velocity, and you integrate this, you get 1, and you should hopefully stop and say, hey, wait, I forgot to multiply by the thing I want the average of. Oh, that actually means I'm solving a d cubed. Oh, look, there is an identity for something that looks like that. Now I'm doing it right. So look out for that. But don't forget, there is a third thing you can do, which is to take the derivative of the Maxwell-Boltzmann distribution, of course with velocity, because that's what it's of, and set it equal to 0, and therefore you get the most probable velocity, which, hell, I forgot what it is. We have a lot of these memorized. I think it's 2 kBt over m. Is that right? I don't quite remember. Hopefully I didn't just completely screw that up. Of course I can do it. These are, remember, if I ask this, thank me. These are actually easy, right? I know they start out looking kind of difficult because you have to do a product rule. But when you set it equal to 0, you actually will see that it's by far the easiest question I could ask. And what that shows you is, here's your most probable, and your average velocity tends to be right about here, and your RMS velocity tends to be here. Of course, I have to set that to the half or it doesn't have the right units. So anyway, remember it's kind of interesting that that gas molecules move faster than the speed of sound. I thought that was kind of neat. Technically, I guess I shouldn't have the integral to infinity. I should have the integral to the speed of light, but it doesn't matter because of this term question.
Why would you use the root mean squared velocity?
Now recall that what we use this for one, there's nothing I can't solve with this. Anything composed of v's I can ask. So I asked, what's the average velocity squared? Why did I do that? And that was because I was able to do this, which is energy, right? And remember that since you say, well, I had average velocity, just square it. This squared is not equal to that. They're not the same. So I had to explicitly solve that. And what did we end up getting? 3 halves kBT? I think that's right. And that would make sense because the equal partition, you figure out the equal partition theorem, right? You get 1/2 kT for every degree of freedom, and this is a perfect gas molecule with 3 degrees of freedom. So that's one of the purposes. So whenever we calculate the average of something, hopefully it has some purpose. We can technically look for the average square root of a velocity. Sure, there's nothing we can't get out of it. I just don't know whether you want to or not. So anyway, all right. Remember these suckers are normalized, but always assume that. I generally don't, and I didn't ask questions about that. You need to multiply by the thing you want. Look for the identity, and look for this one too, right? And this is just, I'm just giving you points. You should be able to do this. It's just, right, I was trying to make sure you can do some basic math there. Any other questions? So let me start on quantum. You know that, so I don't have a lot of time left, which is fine because you probably don't quite remember the Maxwell-Boltzmann as well as quantum. And that's because we just did quantum a few days ago. So, I don't mind answering questions early on because I think this is the part you may have actually started to forget. What I see also, I warned you about this, I see people take Maxwell-Boltzmann distributions and square them, trying to treat it like a wave function, which it isn't. A wave function squared is a Maxwell-Boltzmann distribution. Don't forget that. Anyway, let me just say a little bit about Planck distribution. Obviously, I actually just said a lot about it. But what's kind of interesting is we just talked about the energy. I'll just plot it. Now remember one funny thing about when we plot spectrum as a function of wavelength, that's kind of bad. Chemists plot like UV vis spectra, fluorescent spectra as wavelength. Physicists never do. Physicists have it right because wavelength is not energy. It's not linear. It's not linear with energy. Wavelength is 1 over energy. It's a really bad way to plot things, but chemists traditionally do it that way. It's a little stupid. Okay, so remember that a Planck distribution looks like this. It's a skewed distribution. I think it rises like lambda, 1 over like lambda to the 3rd power, I think, maybe 4th power, I don't remember. Anyway, it rises, and a lot of people knew that back in the 1900s. But it was only when Boltzmann came around and said that, oh, by the way, there is a weighing factor that prevents a light bulb from generating any arbitrarily large amount of energy. This thing causes the spectrum to bend downward again. So when people first started analyzing, I mentioned this in the extra hour, when people started analyzing light bulbs, making sure that they kind of understood how things work, and light bulbs were a thing back in 1900, they first got this part right, but then they simultaneously thought that a light bulb should generate infinite amount of energy, which they don't, and that's obvious. Boltzmann was the one who was able to figure that out by saying, no, that there's a weighing factor That doesn't mean that a light bulb, by virtue of having heat, cannot generate any arbitrarily high energy photon like X-ray or gamma ray. So there was that, and let's see. Okay, last bit, and I've only got 10 minutes, but I can, again, you've already, this last homework, there's a couple of questions on the test that are very similar to this last homework, so that hopefully is enough studying for you. I just want to point out that where quantum mechanics gets its start is in Einstein's theory of relativity, which is this guy here, and I had you do some stuff with this. And remember that what Einstein showed is that with this equation and with the photoelectric effect, when light was hitting electrons, it knocked them around. And that makes sense because photons have energy, and it takes energy to knock things around. But it simultaneously takes momentum, and that was weird. I know that photons have energy, that's obvious, I can feel it. But they also have momentum. Now that's weird because they have no mass, but Einstein's equation predicts that light has momentum. And so that's why it can hit an electron. It has the energy to knock it around and momentum to knock it around. It needs both, and Einstein correctly predicted it did. De Broglie, with a weird spelling, I'm sure that there's way more to this. He ultimately just kind of rearranged this equation and said, well, that anything with momentum, light or stuff, you, the cat, electron, everything has momentum and therefore it has an associated wavelength. Schrodinger and Heisenberg start thinking about how we model things. They were modeling things by what we call fancy pants, classical Newtonian mechanics. Okay, how much does it weigh? What's the acceleration? What's the forces on it? Let's do some calc. We can tell whether it's veering left or right, yada, yada, yada. That's all fine and good, but where's the wavelength? There's none. There's no waviness to it at all. And so they start thinking like, how do I have a model for where something is, but it also has a wavelength associated with it, and it turns out to be this too. How do I satisfy all that? And the answer was, now for one, we started with an expression that kind of makes a lot of sense. Kinetic energy plus potential energy is total energy. Now we haven't gotten to potential energy yet, so let's drop that. So it was all about kinetic energy, and what de Broglie figured out was that if he modeled things with a wave, and cosines are waves, and okay, so let's just start out with that. Let's just say that this is a good model for stuff as anything else. How do you make this consistent with the de Broglie wavelength? Now, if I look at de Broglie and I see that momentum, if momentum is h over lambda, momentum squared is h squared over lambda squared, and therefore momentum squared over 2m, which is kinetic energy, is h squared over 2m lambda squared. Okay, how does he make that happen? How does he make this happen? How does he get this kinetic energy out of this? The answer is, I'll just cut to the chase, he simply has to add the constants, but if he does the double derivative of this sucker, it works. And it also has the correct eigenvalue form, which he knew he needed as well, because he has a differential equation. Differential equations need to have an eigenvalue flavor to them. So let's just double check this.
What's the difference between an eigenvector and an eigenfunction?
What's that?
What's the difference between an eigenvector and an eigenfunction?
Oh, same thing. Sorry, same word for, multiple words for the same thing. I know I've been, unfortunately, going back and forth between those. So 2 pi squared over lambda squared cosine, let me just call it kx. Now remember that h bar squared is h over 2 squared pi squared. That's how that constant is defined. 2 squared pi squared over lambda squared ends up being, double derivative, minus, there's a minus sign. H squared over 2m lambda squared. Right, it's the same thing. Okay, so he gets it. He gets it right. So again, it's kind of engineered. It's engineered. He says that I need to start modeling matter as having waves with wavelengths because Du Bois says things should have wavelengths, so this seems to work, but I need to get the kinetic energy to make sense. This is an engineered thing. It's an engineered thing, but it does engineeringly work. So this was the birth of quantum mechanics. Then, as we're going to do when you come back, you start adding potential energy and solving that SOB, and everything they tried worked. It took them a bit of effort to figure out all this stuff, but yeah, it did work. So recall that everything in quantum mechanics is a matter of an operator acting on an eigenfunction or eigenvector. Sorry, it's the multiple word for the same thing. That's like operators on functions, wave functions, give eigenvalues, which are numbers, times the wave function. When this is the Hamiltonian, we think of it as special, even give it its own symbol, and the guys that are good with the Hamiltonian, we give even also, we give them a separate symbol, and its eigenvalue happens to be energy. Again, we actually have a different little expression when we're talking about Hamiltonian because we think of these as being, these wave functions are the real wave functions. And still though, when we're doing momentum, we need to be able to get, we need to get this to work. If it doesn't work, then it's junk. In which case, if you run into that problem, then what you do is an average value expression where you do it this way, and we talked about how that works. So that's the answer. And we're still in one dimension. We're going to do multiple dimensions literally on Monday after the exam. And the last bit I wanted to point out to you is what's a little funky about this, where this is not quite looking like, now remember that a wave function squared is like a probability distribution. It needs to be normalized. So it looks a lot like Maxwell-Boltzmann again. It looks like probability distribution times the thing you want the average of. And that really is a good way, that's a very accurate way to think about it. Where quantum mechanics, I really don't quite know how they first figured out to do this. You actually end up with the operator in between the two, so it's a little odd in that respect, but it's still pretty similar. It's basically the probability of distribution integrated times the thing you want the average of. So you want to think of it that way. Momentum ends up being a little bit of a Bismarcker because that's a derivative, but you may recall that if you're talking about the x operator is a dumb operator. It doesn't really do anything. It just sits there. So you can separate that one. You can separate that one out. And then you can see a little bit more clearly how you've got probability distribution. You can see how you've got probability distribution times the thing you want the average of. It's of course the average value of x. Anyway, that's how you do that. Just don't forget that the wave function needs to be normalized. And I've already warned you, I do have an average value question on the exam. It's not hard. Wave function, you know the operator, do the calc, find the integral expression, done, full credit. It's not right, it's all basic. Everything you're doing mathematically is just taking derivatives of sine or integrating e to the I kx. It's all, and you're not even doing that. You have identities to do that for you. Last bit, recall that I did this on purpose, and I know it didn't hang up a lot of you. If a wave function is e to the I kx, the wave function, the complex conjugate, is e to the minus I kx. If a wave function is sine kx, And again, you need to know this, what is the complex conjugate?
Sine of kx.
Sine kx. Remember that a complex conjugate, take an I and put a minus sign in front of it. And you're looking at this, a lot of you said, well, but there's no I. Sure, there's no I, so you don't do anything. Right, remember, you always can default to taking me very explicitly. Don't find something that's not there, because then you're changing the question. So you might need to know that as well. Other than that, I think I covered everything. I gave the answer to half the exam, by the way, when I did this, so there you go. Very easy exam.